Good morning, everyone. I hope you're having a great Unreal Fest so far. Looks like a pretty good turnout today. My name is Kevin. I lead one of the rendering teams at Epic.
And my name is Jarosław. I am expert engine core tech engineer at CD Projekt Red, and I'm super excited to be here with Kevin to bring some developer outlook on the topic.
So today we will be taking you behind the scenes of the Witcher 4 Unreal Engine 5 tech demo, which you hopefully saw yesterday. Actually, raise your hands. Who saw this thing yesterday?
Nice.
All right, you've come to the right session for sure. So our main focus today is the performance aspect of the demo, both from the CPU and the GPU side. We'll talk about some new things we did for the demo, and also some general good practices, and hopefully you take away a lot of knowledge of how to get your large open world game to run at 60 FPS on current gen consoles. So here's what's in store for us today. We'll give you a peek at the goals we set up for ourselves at the start of the project to give some context. We'll talk about some of the frame budgeting philosophy, and then move into the details on the key CPU and GPU improvements and how those were implemented in the demo. But first, let's hear a little bit about the collaboration behind the demo.
Yeah, we have been given the great opportunity to combine the best of both worlds, the technical expertise at our friends at Epic with our experience at CD Projekt Red in building big, dense, open world games.
So we've essentially worked as one large team, coming up with solutions together, reviewing each other's work, and generally fought hard to make this into an awesome demo for you guys, but also to improve the engine along the way.
The collaboration was a win-win scenario. Our teams worked together, and because of that, we were able to achieve things that we couldn't if we were separated. Without the groundwork done by Epic Engine core teams, we wouldn't be able to build all the game systems that were necessary to bring demo to life. During the sessions, we're gonna talk that we did things together and we're gonna with you indistinctively. But the credits has to go where the credits are due and to the both sides, because the work was very collaborative.
So what is this demo exactly? Well, it's an open world tech demo running on PS5 at 60 FPS with all the latest Unreal Engine 5 features. We've done some awesome demos in the past to showcase Unreal Engine, but now was the time to really push the core of the engine and focus on that 60 FPS in performance in general. Note that this demo showcases the current tech of the current state of the tech, and it's not the final representation of the Witcher 4 game.
We aimed at 60 FPS because it strikes a balance. On one hand, it creates much smoother appearance than lower 40 or 30 FPS. On the other, it still gives us plenty of room for stunning visuals. We wanted to reach it on the current gen consoles so we can make sure that it's attainable on the hardware and displays widely available in our living rooms. The key goal of the demo was to bring the hardware ray-traced global illumination for specular and diffuse lighting in 60 FPS, so we can support the dynamic day and night cycle and moving objects in reflection in really high details. We wanted to build a technical backbone for building dense dynamic forest with all needed pipelines to support it along all the render passes, with all the pipelines to alter the asset and assemble the scene. We especially focused on spruce trees. It is not only because it's one of the most common tree types in a Witcher home country, but also because this is one of the most challenging tree species we can have. We knew that we have to be able to build it at scale. The demo run showcases just a fraction of the world we built, of the world we created. We built up the forest up to horizon with many organic, beautiful environment spots. But we still have been able to provide a hitch-free experience to fulfill this roaming Witcher fantasy we have, where the technical limitations do not interfere with the joy of the Kelpie ride. So when we finally approach the Vardrest, we can present you with the place that seems to have a life of its own, where the Ciri is just a visitor, but she still can cross her paths with NPCs' daily routines. We knew it will be only possible if we will focus on better hardware utilization. We spent a lot of time on removing things from the critical path and running them asynchronously, but also in parallel. We have been working on the technical demo, but the technology we are trying to build is meant for a full-fledged WeChat game. So we had to ensure that we know how we will be able to scale into full gameplay features. We built with consoles limitation in mind, but all the changes we did will benefit PC or any future hardware. So how we approach that? When you build an open world experience, one of the most important concepts is budgeting. When running at 60 FPS, we have just 16.6 milliseconds to simulate the scene. We have 16.6 milliseconds to prepare the data for the GPU, and then 16.6 milliseconds to render the scene in the best quality we possibly can. Our role as engineers is to help our gameplay and art departments to understand the scene they are trying to build, on what engine features they should focus so they can magnify the artistic vision they have without sacrificing the image quality and frame rate. In case of our demo, we can recognize at least two major scene types. The first one is cover wilderness. It is full of natural moving foliage, full of details, density, with gorgeous lighting and crisp shadows. It heavily relies on volumetric effects for immersion to evoke the sense of wonder. But it's also a significant part of the long vista shot in the world that has to invite you to explore. We had to be able to build it at scale, carefully balancing handcrafted areas with offline and runtime PCG scattering. We had to ensure that the traveling is not the chore, but rather a smooth experience. The second scene type we have is our well-dressed market. The whole area is with much shorter vision range. We focus there on NPC, on the quality of the animation, and the simulation of their daily routines. We want to ensure the quality of animation allows us to present them and put them into situations where we can have dynamic interactions. But the tech demo is not only about balancing those features and picking battles, it's also about pushing for things that we couldn't afford before. Sometimes due to hardware limitations, sometimes due to limitation of the implementation itself. To make that happen, we prepared a lot of the tech that will be showcased on AnnuFest on Orlando, and I highly recommend at least those 3 talks that will go deeper into things that we wouldn't be able to explore today. But now, I would like to take you behind the scene of our most CPU-intensive frames, where we have our market bid with 300 NPCs. But the topic, it's gonna be very complex, and we won't be able to get into a lot of details. I will showcase the Annual Insight frame, but the frame itself won't tell you much. Before we jump into those details, I will try to make a short breakdown with high-level approach, what you're gonna see in the final picture. I will start with those threads. Every line represents single thread of execution. And we have our GPU that renders the scene. In case of our demo, we run configuration in which GameThread is simulating frame number n. Render frame is frame behind with n-1, and GPU runs 2 frames behind. This setup was needed for us to ensure that we handle any unexpected 1-frame hitch that you can always expect in open world games. But diving into game frame execution. Everything starts with QTix. It handles execution orders, kickstart all the game systems that need to run this frame. And immediately, our demo execution separates execution in 2 ways. We have classical GameThread objects update, but also at the same time, we span dozens of game update state tasks that run concurrently on the worker threads. Those tasks govern logic of the demo, AI behavior, smart objects interactions, and are even responsible for ticking skeletal meshes. With skeletal mesh updates, time comes for animation update. And to finish animation update, we have to inject finalization tasks back into the game thread to synchronize the state with all other engine systems. With root motion extracted from those animations, now we can combine it with pathfinding information. We can combine it with pathfinding information that will interleave with animation evaluation process. It doesn't have to wait for all animation to finish. And once again, to finalize that process, we inject finalization tasks back to the game thread. Now, time comes for game thread system updates. We still rely on quite a few game thread-bound systems like streaming, PCG generation, and timer manager. And finally, game simulation ends with end-of-frame update, where we prepare all the data that is needed to send to the GPU, and we kickstart next frame. But now, we will start process and preparing the data on the render thread side, starting with just received data from the game thread, all the updates we got. Next, we update the visibility, Lumen, we update the GPU data for our primitives, and we start building render dependency graph. We execute a bunch of ray tracing related processing tasks that once again can run in parallel. And finally, we execute RDG that will span dozens of parallel execution tasks. If we look at this frame from the perspective of just that slide, it all seems quite straightforward. But we omit here a lot of the details. Some of the things are hidden behind the abstraction, and we don't include here things like asynchronous loading, audio system, or texture streaming, or physics. We wouldn't be able to fit them all in such a simplified slide. The full frame with all important information looks more like that. So I am really hopeful that you are already familiar with Unreal Insight. And with the context of the bit we just did, I will try to retrace my steps and go through the frame once again. So we have our QTix. In case of our demo, it manages 2,500 of the ticking objects across all those threads. It was possible due to changes to Tick Task Manager that added better support for worker thread ticking objects. And we handle state update. To handle state update, we heavily rely on mass systems. It is responsible for things like LOD changes for NPC, pathfinding, smart objects interactions. But special attention deserves mass to AnimNext translator. This processor, it's not only governs the update for the skeletal meshes, but also it replaces a tick behavior for our crowd skeletal meshes. It is responsible for ticking over 800 skeletal meshes each frame. To evaluate the animation, we are relying on Unreal Animation Framework, or as it was previously known, AnimNext. It is responsible for evaluating over 400 animation graphs for our skeletal meshes, with around 54 milliseconds of parallel work and just 2.6 milliseconds of finalization tasks on a game thread. And once again, I recommend dedicated session for this. Coming next, Mover, with simulation in parallel and just 1.3 milliseconds of finalization tasks on a game thread, with yet another reminder that there is a talk that you should definitely see on the topic. And we end game frame with end-of-frame updates. The implementation was overhauled, and now it should scale much better with CPU core count. For rendering update, I will just point out skeletal mesh update optimization. With processing removed from critical path, we have just around 3 milliseconds of processing on the render thread side for all the crowd-related skeletal meshes. The whole demo uses ray tracing. So to be able to catch up with our fast-moving scenes where we have around 20,000 primitives and hundreds of thousands of instances, we had to ensure that the gathering and the processing of data is up to the task. The execution was removed from the critical path and now run in parallel. Changes were made to increase render dependency graph processing capabilities. And again, especially worth noting, parallel command list translations. With over 16 milliseconds worth of work, we would be RHI bound if those changes wouldn't be implemented. With 13 CPU cores available for us on a console, here each is represented as a color where basically the color represents occupancy of the given CPU at that specific moment. We reached around 87% utilization of all available cycles. Of course, we still have room for improvement. At the beginning of the frame, we cannot too late saturate workers with tasks. And again, during physics, we wait for those final animation and movement updates to finish before we go to the next stage of the frame. And finally, there is this short space when we submit, where we have RHI submission tasks. Nothing interleaves with that. But going back to our frame, how we can put the gameplay into that specific frame. In this scenario, we have actually on the game thread around 2 milliseconds worth of waits on our critical path as we wait for those animations and movement finalization tasks. Combining it with 13% of the CPU utilization left, we can redirect some of those cycles into limited gameplay functionality, pushing the animation evaluation towards this gap that we have during physics. But if we change the balance of the crowd a bit, if we just see 200 instead of 300 NPCs, we greatly reduce the game frame time to just 11.5 milliseconds. As we reduce the number of evaluated animations and we remove the real NPCs and just simulate so-called stubs. If we count all the empty spaces that we have during the frame, it's like 1 millisecond worth of waits, and at the end we actually have 5 milliseconds left before our 16.6 millisecond limit surpasses. And actually, if you look at the whole CPU utilization, it gets lower to 60%. We have those 4 quite a big gaps that we see that we represent here on the presentation, and we believe we can build much more complex gameplay systems due to those additional cycles. We see this as a good prognosis that what we build has a room to grow, and we have some ideas how we can implement much deeper gameplay systems.
All right, let's take a look at what we did to achieve 60 on the GPU on a current gen console with Lumen using hardware ray tracing for both global illumination and reflections. And we made it even more challenging by adding a dense dynamic forest into the mix, all rendered with brand new Nanite tech. So now that you have Unreal Insights seared into your retinas from that last section, let's take a look at some more Unreal Insights. Let's start with a very important topic for performance, profiling. So profiling and knowing your data is key for understanding how to optimize. This begins with having all of the data. So with 5.6, we bring you a brand new GPU profiler backend, which is more accurate and can report much more data to Unreal Insights. So this screenshot here shows you 2 GPU tracks in Unreal Insights, where you might have been used to only seeing one. Top one is the graphics queue. This is what you were used to. And the bottom one is the asynchronous compute queue. So this was not possible to display before, and it wasn't really telling the whole story then, but now it is. Another new feature are these red arrows showing dependencies between selected events. So you can clearly understand the flow and scheduling of GPU events between queues throughout the frame. The improvements here aren't limited to Unreal Insights either. Like you'll get better GPU reporting from stat GPU and profile GPU, or you'll be able to see weights and other timings instead of just the raw executed time. So if you're not using Unreal Insights for GPU profiling, this is the time to start. And let's talk about this asynchronous compute, or async compute as I'm going to call it. The very basic explanation is that you can optionally launch compute work on a separate queue next to the graphics queue. This will give the GPU a chance to overlap compute with graphics work when there's room for both. And oftentimes there is room, since shaders are never really scheduled with 100% resource utilization. So this gives us a way to shorten the overall frame by going a little wider. Now with this crash course in our bag, let's compare a frame with and without the async compute enabled. So at a quick glance, we see that this gives us about 1.5 milliseconds back in total. Not bad. And if we start looking a little closer, we can see that many of the passes that we offload to async compute start at very different locations in the frame, and they run for much longer. But that's okay, as we're now running together with other things. We're overlapping this work. This makes it harder to compare the cost of individual passes, of course, since they kind of grow and they overlap with other things. So if you want to profile individual passes and know how long they take, you still have to disable async compute for this. You can also see that this allows the queues to start at different points, meaning some of the work of this frame could have started overlapping work from previous frames. And that way we can utilize the GPU to its fullest, even at the very end of the frame, where it's typically hard to find meaningfully overlapping work. So now, for this particular demo, what's new? So if we zoom in a little bit, we can see this part here, where we now run the GPU skin cache jobs on the async compute queue. That's the underlined at the bottom there. And as the arrows show, this work overlaps with the previous frame post-processing, where we didn't really have anything to overlap before. We also offloaded a few more things to the async compute queue, like the wind simulation, and we actually ended up moving Lumen reflections back to the graphics queue, which in our case saved us time because we didn't have enough stuff to overlap with. So that's a lesson to simply not throw everything at the async compute queue, because if there's nothing to overlap with, it can actually backfire and cost you some extra. So it's important that you profile your particular setup, and you can now do that with a new GPU profiler. So, recommended that you take a look at how things are scheduled in your particular case, with your particular content. It might be different from what we've set up the defaults to be. And a lot of the rendering features have CVARs to control the enable, disable async compute. So you can actually play with this yourself and look at insights now to see how things are scheduled. Note that not every GPU supports this, but all the newer GPUs, new consoles, most previous gen consoles, etc. do. So it's a pretty good idea to have a look. All right, now it's time for some features. At the beginning of the project, right, we saw it was pretty obvious that rendering foliage the old way wasn't really an option. As the team were facing pretty tough requirements with high density forests in an open world with quality never seen before, all running at 60 FPS on a PS5. So let me first explain here how the old way didn't really cut it. So Nanite doesn't like alpha mask geometry, as it introduces overdraw in addition to having to execute a potentially expensive opacity mask function. Also, we don't want to be forced to render foliage as flat cards now that we know what Nanite is capable of complexity-wise. So what about triangles then? Well, imagine hundreds of thousands of pine needles modeled as geometry. That would cause suboptimal cluster culling and poor simplification in the distance with today's Nanite. I know we have the preserve area option on the mesh to combat some of this, but it isn't perfect. And also, if these are all unique triangles in a tree, the assets on disk would be absolutely massive. And for wind, we used to rely on world position offset in the material to move leaves and branches. I'm sure many of you are doing that right now. It's pretty common. Well, it's not a great match for Nanite either, since it adds per vertex calculations and forces suboptimal cluster bounds. Since we don't know how a material will move the vertex, we have to be very conservative in how those bounds are set up. So what's the solution? Well, the team embarked on a lengthy research effort and ended up with this: an all-new rendering pipeline within Nanite to enable rendering fully modeled trees down to the individual pine needle, while also scaling to large open worlds, be memory efficient, performant, highly dynamic, and without the need for LODs, the Nanite way. So, to combat disk size constraints, the new Nanite Assemblies feature allows us to build up a tree out of a set of instance branches, which means we can have very large trees with very detailed quality at the same time. In the distance, Nanite will start rendering voxels instead of triangles seamlessly to solve the problem of rendering dense and dynamic aggregate triangle meshes. These voxels are imperceptible to the eye as they will be pixel-sized. And wind is simulated through a bone hierarchy, as these are skeletal meshes. No more world position offset, and we can use fixed function nanite with optimal cluster bounds. So here's a brief demonstration of a tree created and rendered with this tech. This is the pine tree we showcased in the demo up close. We call this the hero tree. And as you can see, going from up close with individual pine needles to far away is seamless. And while you can't tell, it's actually rendered using voxels once nanite clusters become small enough. So this allows us to keep that volumetric tree look and not have to resort to billboards or LODs or anything baked in the distance. And here it is again in its full glory. It's made out of 41 million total triangles across 12 instance assembly parts, with a total of over 2,000 of these assembly parts instanced. And all that with 850 bones in the skeleton. And to the left here, you can see two examples of what an assembly part might look like for this tree. And you just use these parts to build up the tree. And let's look at some numbers from the demo. So this here is the vista shot of the forest that you saw in the demo. In this vista shot, we are rendering about 20,000 trees with a source triangle count in the billions, right? But it doesn't really matter because this is all nanite. Across the whole valley, we scattered over 100,000 trees and shrubs across 28 species and multiple biomes. And tree assets actually range from the 1 million to above 10 million triangles in the general case. They're a little bit smaller than the hero tree. And they have several hundred skeletal bones, depending on the species and the size of the tree, of course. And this is where nanite assemblies really help, as we can reuse branches and twigs to build up a tree. And the wind simulation is driven by a wind compute shader, which runs wind procedurally and applies it to the skeletal bones. In this shot, we're updating about 100,000 bones, which takes about 0.1 milliseconds on the GPU, so it's very fast and scalable. And animation stops being applied automatically on trees below a certain screen size, which effectively brings the wind pretty far out into the distance for better immersion. This also applies to grass and shrubs, which are also skeletal meshes. So a little disclaimer here before we move on. Since this tech needs a little more time in the oven, it isn't coming with 5.6, but will instead soon drop into UE5 mainline in preparation for 5.7. So the early birds out there could give it a try on GitHub. And once ready though, we plan on supporting it with great example content directly downloadable from Fab, so you can start playing with it when available. And while we're on the topic of nanite, I'd like to drop some performance tips and tricks that helps us along the way on this project. So Nanite renders a lot of its triangles using software rasterization in compute. That's kind of the secret sauce. So we're not bound by the hardware requirements of having to calculate derivatives using a 2x2 pixel helper lane. What we do is we figure out if the material can safely use analytical derivatives instead, and therefore skip launching any of these helper lanes. And this can drastically reduce the number of pixel shader invocations in your frame, but only if your material can support this. And you can check what objects are contributing to launching these helper lanes with this debug view mode here. And Nanite stats will also show you the number of helper lanes that you have going on. And getting this close to 0 is the goal. Also, whenever possible, try to avoid making your Nanite materials programmable. This is when you are using material features which aren't supported in the fixed function fast path of Nanite, like masked, world position offset, or pixel depth offset. You can easily see what is taking the fast path or not using this debug view mode here, pixel programmable. And be careful with Nanite tessellation. It's not free. Make sure you set up your displacement range in the material that fits the actually intended displacement. Otherwise, you're just expanding the bounds of these clusters more than necessary. In this demo, we actually only use Nanite tessellation for the landscape. And in general, you want your meshes and materials to support Nanite as much as possible where it makes sense. So be on the lookout for objects which might not have been set up correctly for that, and you can use the Nanite mask view mode. So green is good in this case, and there's some water there which doesn't support it, and some Niagara birds. All right, that's it for Nanite. Let's look at Lumen and hardware ray tracing. So here's a shot in the village showing what the ray tracing scene instances look like. We keep the near field loaded to up about 150 meters, which includes landscape, foliage, static, and dynamic geometry. We have a ray tracing geometry pool budget of about 400 megabytes, but mostly peak around 300. And we budgeted for half a millisecond roughly in ray tracing scene updates on the GPU, and it's all running on Async Compute. And so that's the near field up to 150 meters. What do we then do beyond that? Well, that's the far field, and it's a separate set of proxies far away that we use for tracing faster rays over longer distances. This is set up as a separate top-level acceleration structure, so we can start by tracing the near field here and be smart about it, and then decide if we need to go further into the far field. It contains only static geometry, so we don't have to update it every frame, and typically this is stuff like HLOD or landscape or larger set pieces in general. And in Lumen, we can actually make use of the far field as an optimization. So we've introduced a mode where we can trace only for occlusion in the far field and not have to pay the cost for lighting those hits. So in the village, we have another challenge, animated characters, and there are a lot of them. We can't simply keep them static, right? Because they would be T-posed in the RT scene and it would mismatch what we see. So what we do is we stagger the updates to about 40,000 dynamic triangles per frame. And we update the most important characters only, and these are the ones nearby. So we know that by adding more characters to the scene, we don't blow the budget as they come on screen. Under the hood, there were several other improvements in this area as well. So running the GPU skin cache on the Async Compute is one I mentioned earlier. Another one is actually tying the GPU skin cache to the ray tracing scene updates. That way we don't spend cycles filling up the skin cache with meshes we're not going to use. And landscape, it's also a pretty big part of the dynamic instances, as you can tell from this debug viewport here. Like they're green as well as the characters. It's actually a pretty large chunk of the dynamic instance budget, so it has its own time-sliced update on LOD changes, and in general, we have a lower LOD for the landscape as well, so it's faster to trace and faster to update. As the dynamic budget is very tight, we opted to not animate the trees in the ray tracing scene. So to make tracing the forest and allowing for the right amount of light occlusion, we created a special path for building ray tracing proxies for foliage specifically. And this effectively takes the source mesh and generates a triangle cloud to match the occlusion density needed for indirect lighting. So for the 41 million triangle hero tree, that can end up with as few as 225 triangles in the ray tracing representation, which does what we need for the lighting and the occlusion, but it's obviously not going to look great in a mirror reflection because you would see those triangles there. But for our purposes of hitting 60 FPS on current gen consoles with a massive forest, this is a pretty good compromise. And even on water reflections, actually, it looks all right because there's always some movement in there, normal maps and waves. So here I highlight the main Lumen passes. So we got Lumen scene lighting, Lumen screen probe gather, Lumen reflections, just to get an idea of where Lumen contributes to the frame here. And this is with Async Compute disabled, so you actually see the real kind of sizes of these boxes. And there are a few more. These are updating Lumen cards. There's a second Lumen reflection pass inside of single layer water, and I also included the ray tracing scene update here. And as you can see, Lumen and hardware ray tracing are central parts of the frame budget, and there's a lot of performance to be gained here by paying attention to your content and setting it up properly. Let's look at a few performance pitfall examples and how we solve them. So here's a view in Valdrest, the village, with various reflective puddles. It's not an uncommon view. And Lumen can trace dedicated hardware-accelerated rays for each reflective pixel, which can be very expensive, especially on platforms and graphics cards that don't have all that much ray tracing power. So the solution here is to set up an appropriate roughness threshold. This means that roughness values of your materials above a certain threshold will, instead of tracing the expensive rays, fall back and get the data from the Lumen Radiance cache, which is much less detailed, but also much faster. And here's what that looks like. We got a 0.4 threshold versus a 1, which is no threshold effectively. It's pretty much imperceptible difference, but well worth being 3 times faster in this example. There's also the option to set up separate thresholds for foliage, because you might have different considerations for that type of content. So you can easily figure this out by looking at the debug view modes to show pixels that are actually tracing the expensive path. You can also look at the Lumen reflection passes in Unreal Insights now to see if they're expensive or not. I guess that's the most important bit to look at. And another one worth mentioning here is the water reflections on single layer water shading model. So there's a large chance that your game or project has water in there, and we actually always trace these dedicated expensive rays on water. So what's easy to forget here is that we're also lighting what's underneath the water. You can't see it here, but there's stuff under here. When the passes before, we actually render that, we light it, and then we just put water on top, and we render that, and we light that as well. And what's even worse is, obviously, your materials around the water, under the water, are typically very wet. So they will be below that roughness threshold, again, triggering those expensive reflections from last example. So we introduced an optimization here where you can provide a depth value where water is considered opaque. And we can call all Lumen contributions under that, making for significant optimizations in deeper waters. So this is the mask where we don't calculate the lighting below water. And in this shot, we save well above a millisecond because pretty much all the water is deeper than the threshold. But obviously, if this was shallow water, like a river or a creek up the mountain, this optimization wouldn't apply. So don't forget to profile your content here. All right, as we leave this section, I want to touch on Lumen hardware versus software tracing. It is particularly important to differentiate between the two, since both approaches fundamentally trace against different representations and have different feature sets. It's really difficult to author lighting for everything once and just have it work out of the box for both paths. And since hardware ray tracing is what we consider to be the future of Lumen, we've gone all in on optimizing that to be usable on consoles on 60 FPS. And there are also several improvements in hardware over software. Other than the higher quality, we can trace skeletal meshes. You're no longer reliant on the static distance field, so you can remove those and save a ton of memory. So the choice should be pretty clear, right? At least we do recommend hardware ray tracing going forward. And as proof of our claims, other than this demo, of course, we have been shipping hardware ray tracing Lumen on current-gen consoles in Fortnite since last December at 60 FPS. So whether you're getting started or are looking to switch a project from software to hardware tracing, I highly recommend our Lumen and hardware ray tracing performance guides in our official documentation. These are packed with good stuff. So with that said, 5.6 brings a very long list of Lumen optimizations, far too many for me to go through in this session. So we'll leave it at that for now, but you can go to the release notes and read about all it. Virtual shadow maps go hand in hand with Nanite, and we've been hard at work at optimizing shadow map rendering for large open world dense forest games. First of all, Nanite voxel representation already helps here because it's also fast to render in the shadow maps. On top of that, there are several other bespoke optimizations which help out in more dynamic scenes. One big one we call receiver masks. It's essentially creating a tighter culling by subdividing each VSM page into 64 tiles. And in this shot, it brings the Nanite VSM shadow depth cost down significantly. And it doesn't really change any of the visuals, so you don't have to worry about it. It's just faster. And for trees, as I mentioned before, we automatically stop animating them in the distance based on screen size. So we can actually make use of this in the shadow rendering by making the non-animating trees statically cached, so we don't have to keep rendering them when they're really far away. We've added a few more tricks to VSM when it comes to automatically balancing quality and performance, like automatically lowering the VSM quality in areas that are out of focus from depth of field. And this helps greatly to lower the costs and make room for higher quality effects in cinematic conversations, for example. As you can see here, all the blur in the background, you don't need the highest quality shadows there potentially. And since it's hard to control every single frame in an open world game, we often see some areas being more expensive than others. This is especially true for shadow rendering, as it's dependent on a lot of factors like sun angle, how close to the shadow receivers you are, and many more things. Normally, to compensate for this, we use dynamic resolution, which works well to absorb temporary expensive parts of the frame. The downside is that if the shadow rendering becomes expensive, the whole frame lowers resolution to compensate, which is not always a fair trade-off. So we've introduced a VSM throttling system where only the VSM quality will lower when going over shadow budgets. This way, we can keep things crisp in the general case and mitigate performance issues stemming from VSM, specifically when needed. So last item I'll mention on VSMs is to give some love to the non-nanite skinned meshes. So this is an optimization where we simply recompute the mesh bounds at runtime inside of the GPU skin cache shader. Since we're already touching all those vertices there anyway, we can just make the bounds up and send them to the next pass. And this leads to significantly more optimal bounds, and it's independent from the content, which is great because now it just kind of works. And there's been a whole host of not so visible general optimizations as well to shave off costs where it matters, especially when it comes to dynamic time of day and dynamic scenes. So we are working very hard to shift the core philosophy of VSM perf mainly being about static caching to being able to perform out of the box with dynamic time of day scenes as well. All right, so what about performance when it comes to resolution then? So how does TSR fit into all of this? Let's take a look at the resolution through the pipeline here. So this is a totally vanilla frame with no upscaling or fancy resolution tricks. Very simplified, of course. Most of the frame is hidden away in that geometry box to the left. So the x-axis here, you can see it at the bottom. It shows the GPU frame, how it flows towards the right. The height of the boxes denote the resolution. Things will not be fully to scale here, but it's for demonstration purposes, of course. So let's save some perf here by rendering most of the frame at a lower resolution and introduce TSR to upscale. This is a pretty standard setup. We'll call this the primary resolution. And this is great. Now we can actually render even more stuff in our scene as Nanite and virtual shadow maps scale with primary resolution. But let's say we have a large open world game with frame times that vary a lot across the world. It's almost impossible to optimize every single frame in your dynamic game to perform exactly the same. So we introduce dynamic resolution instead of a fixed primary resolution. So dynamic resolution helps you to even out the bumps and keep your frame rate in budget. It doesn't solve any of the hitching, potentially, as it only looks at historical frame costs, but you can configure the headroom in the dynamic resolution if you want to leave room for more hitching. We ended up setting a dynamic resolution range of 800 to 1080p, and these are not entirely arbitrary numbers. For one, your max resolution determines the memory usage of all your screen buffers, but more importantly, TSR can't upscale endlessly, of course. So 2x upscaling is a pretty good spot for TSR. And if we look at this now, as you can see here, after TSR, we still run a bunch of passes at full final output resolution, in this case 4K, and that's pretty expensive. So let's introduce secondary screen percentage. So this is where we use TSR to upscale to a lower resolution than the final output resolution, let's say 1440p instead of 4K. Then we run all those end of frame passes at that slightly lower resolution instead. And this saves you a lot more than just, the TSR pass cost. And as a final step here, to get to 4K, we do a spatial upscale from 1440p to 4K. And this is roughly the setup we use for the demo. So let's compare the cost with and without this secondary screen percentage. So to the left here, TSR goes from 1080 to 4K, and thus runs all of those end of frame passes at the more expensive 4K resolution. On the right, we upscale from 1080 to 1440. We do these passes at 1440, and then we upscale to 4K before the UI. So in this case, it saves us almost a whole millisecond. In a 16.6 millisecond frame, that's pretty big. So quality obviously does take a hit, but it's a better hit than letting your dynamic resolution absorb this cost. If you reduce the primary rendering resolution, you'll probably end up dropping below that 2x ideal TSR upscale and have worse quality. All right, so you might be asking yourselves, with all these new features, the right settings for upscaling and resolution and dynamic resolution, are we hitting a solid 60? Yes, but let's talk about hitches. So as I mentioned before, dynamic resolution works by measuring the cost of past frames to determine the resolution we need to keep the next frames in budget. So if there's suddenly a frame with an outsized cost, it's not going to have time to react and mitigate, so we run the risk of dropping a frame. And if this happens regularly, it can negatively impact the experience and make it feel inconsistent. This is what we call hitching. And the source of these hitches on the GPU can be a number of things, like spawning expensive effects or some larger buffer reallocation. And a very common one is camera cuts, because we rely on previous frame data to effectively do occlusion culling. And if the camera swaps to some other random view, we lose all that data, and we have to render a lot more things with a lot more overdraw. Cinematics and conversations are typical examples of this, like this one where this merchant gets devoured by the manticore. And to combat this, we've introduced a system which will prime the lost data after a camera cut with lower resolution data from the ray tracing scene. This way, we don't simply resort to nothing after a camera cut, but instead have at least something to fall back on. So the images here, they show the Nanite overdraw debug view mode in the one frame after a camera cut. And as you can see, we have a much more healthy situation after priming it. It's still not perfect. I mean, this should be much cooler, ideally, but it's much better than this without the priming. So if you're interested in hitches, or rather the removal of hitches, I highly recommend checking out Ari's talk here at Unreal Fest this afternoon. And with that, we've reached the end. I thank you all for listening, and we also thank the whole team who worked incredibly hard on this demo to make all these improvements possible.
And I would like to thank Kevin and our friends at Epic for inviting me here today.
Yep. I think we've pretty much run out of time on this stage today, so we will be available at the Dev Hub after a short break. If you have any questions, come to talk to us. We'll answer everything. That's it. Thank you, everybody.
Thank you.